Thank you, Lindsay, and good morning, everybody. First and foremost, if anybody has trouble seeing me in a little field of view up in your screen share, if you can't see my presentation or if you can't hear me, please notify Lindsay via the chat button immediately. But welcome everybody to the webinar this morning, Air Void Systematics of Hardened Concrete. Again, my name is Dr. Christopher Kelson. I'm Senior Geologist here at Atlantic Testing Laboratories. I do anything and everything with respect to petrography and geology here in the company, and doing air void analysis of concrete is one of the jobs that I do, and that's what we want to talk about today. So, as Lindsay mentioned, there will be some questions interspersed throughout the webinar, and you'll have 45 seconds to answer them before we move on. So make sure that you see them and answer them as fast as you can. And also, if you have any questions or comments during the presentation, please submit them via the chat button to Lindsay, and she'll read them to me at the end. Also, Mr. Steve Moore, Senior Engineer here at ATL, will be joining us at the very end to help answer questions if need be. So with that being said, just let me also point out that the only way I can point to specific bits and pieces of these images is the use of my mouse cursor. So please watch for that as I point out different features as we go along. So to give a quick definition of what it is we're talking about, we're talking about air voids in concrete. Here's the ASTM definition of concrete. We all know what it is. There's the official definition of what it is. It's important to understand that concrete is the single most widely used building material in the world, with the equivalent of over 913 Panama canals placed every year. That's over 5 billion cubic yards. Now for a quick definition of an air void, it's simply the small space enclosed by the cement paste in hardened concrete and occupied by air currently. Right, it may have been full of water when the concrete was placed, but now it's full of air. The image you see in front of you is a piece of concrete that's been cut and polished. There's a scale bar for reference up in the upper right corner, and you can make out the individual air voids. Different sizes, different shapes, but you get the idea. So air voids come in one of three flavors with respect to concrete. There are capillary voids, entrapped voids, and entrained voids. And we'll touch on all three to start with. Understand that for every 1 cubic yard of concrete, you may have anywhere between 10 and 15 billion voids in that 1 cubic yard of concrete. So they are common features, although most of the time we just can't see them because they're so small. Let's start off with defining what a capillary void is. By definition, a capillary void is less than 5 microns in size. Remember, a micron is a millionth of a meter. These guys are irregularly shaped and form when cement particles hydrate. Originally, they're filled with water or gas at the time of their formation, and generally speaking, the higher the water-cement ratio is in the cement paste, the more capillary voids you'll tend to have. Also, because capillary voids are so small, they're typically not counted in an air void analysis just because they're so small and hard to see, but they're there. Second type of void is what we call an entrapped void. By definition, these guys are greater than 1 millimeter in size, and entrapped air voids come in one of three different varieties, and you can distinguish one from another based on the shape of the void. So an entrapped void that's more or less spherically shaped, we'll call that an entrapped air void. An entrapped water void is one that has a little bit more of an irregular shape to it, even though now it's air in the hardened concrete. When it was in place, it was full of water. And then a boundary void, which is flat. It's flat shaped and located at the boundary between the paste and the aggregates. I'll show you some pictures here in a second. It's important to understand that for the entrapped air voids, they're non-homogeneously distributed throughout the cement paste. Again, I'll show you a picture of what that means, and also understand that these are, as the name implies, the entrapped voids are basically formed when air and or water is trapped within fresh concrete during placement or mixing or agitation or curing. So they're just there. They just form naturally when the concrete's placed. This image is a piece of concrete core that's 4 inches wide, right? 4 inches diameter, and 6 or 7 inches long. There's a scale bar down at the bottom. I've cut this piece of concrete core and I've polished it to really show some detail. And I've also applied a fine yellow powder to the surface, which has filled in all of the big voids. So what we're seeing here is the distribution, rough distribution of entrapped air voids in that piece of concrete. Notice again, notice the scale bar at the bottom. Greater than 1 millimeter is an entrapped void. So some of these are clearly bigger than 1 millimeter. And notice, certain parts of the core have a lot of them. Other parts of the concrete have relatively few of them. So again, non-homogeneous distribution throughout. And the yellow is just for visual aid in seeing this with your eyeball. That same image is at the top of this slide. And for comparison, I've included a picture of a piece of cut and polished concrete that has not only entrapped air, but also entrained air, or a lot more air in any case. And the air voids in the bottom example are full of a white material to visually stand out to your eyeball. So you can see the difference in distribution of air voids and sizes and types. This is another slide showing an entrapped air void. We're looking at a microscope slide made of concrete. So it's a piece of glass with a 25 micron thick piece of concrete glued to it. We're looking at it through the microscope, and all of the open spaces within the concrete are filled with pink epoxy, again to really make them stand out. So the large kind of spherical shape we see up in the upper left, that's clearly an entrapped air void by size, scale bar down at the bottom. And also the shape tells us this was probably initially filled with water when it was formed. But you can see throughout the paste, which is the fine kind of featureless black colored material holding all the aggregates together, you can see that the voids come in different sizes and shapes. Some are spherical, some are non-spherical, some are really non-spherical. So just your eyeball can pick out entrapped versus entrained, which are less than 1 millimeter in size. Just before I move on to that topic, here's another slide. This is an example of a boundary void. So this is an entrapped air void that formed between or along the boundary between the paste and this aggregate particle, and its flat morphology tells us it's obviously in this location, tells us it's a boundary void. So that may have been filled with air or water when it was fresh concrete, but no longer, it's just air. But again, next to it we see some spherical air voids, right? There's a semi-spherical one. So again, typical examples of air voids, how they look. The third type of void that we'll talk about are what are called the entrained air voids. Again, by definition, these are defined by sizes. So anything between 5 microns up to 1 millimeter in diameter are what are called entrained air voids. They're also spherical in shape. They're round. For reference, think of a head of a pin occupying a diameter about 1.5, having a diameter of about 1.5 millimeters. So entrained air voids are slightly smaller than the head of a pin. And for every cubic inch of concrete, we may have, up to 1 million, maybe over 1 million of entrained air voids. So entrained air voids are designed to be there. They didn't just happen to form when the concrete was placed. These are there by design. These represent air that is retained and trapped within the paste via the use of admixtures or surfactants. And the whole point of entrained air is to increase the amount of air in the concrete. Again, here's a slide looking down, or a microscope slide. We're looking down the microscope. Everywhere you see pink, that's an open air void. This is a great example of entrained air voids. They're all smaller than 1 millimeter, homogeneously distributed throughout the paste, and yeah, so a good example of entrained air. Also notice one other thing. Look at the bottom center of the photograph as I'm indicating with my mouse cursor. This is an aggregate particle that has a crack in it, and the crack has been filled in with the pink epoxy. When we do an air void analysis of the concrete, we ignore the aggregates, in the sense that if the aggregates themselves have holes or cracks in them or open spaces, we don't count them as part of the analysis. So this crack is there, but we wouldn't consider it as in the air void test. Okay, time for question number 1.
All right, Chris.
Thank you.
Everyone's finished.
Okay, thanks. All right, so question number 1, what type of void is greater than 1 millimeter in size and possesses an irregular or non-spherical shape? Of course, that's the entrapped air void, option C. So are air voids in concrete good or bad? Well, the air voids in concrete present a double-edged sword, essentially. The good aspects of the air voids, I'll list them here. Number 1, especially with the entrained air voids, they help the concrete resist freeze-thaw damage. That's the big reason behind entraining your concrete with air, so that it can resist freeze-thaw damage and chemical attack. But freeze-thaw damage is the big one. I'll elaborate on that in a second. The more air you have in the concrete, you're obviously reducing the overall weight of the concrete. There's a point where that's counterproductive, but generally speaking, the more air you have, the less your concrete will weigh. Number 3, the more air you have in your concrete, you can still be able to work the concrete, but with a lower WC, lower water to cement ratio. And a lower water cement ratio is good because A, it makes the concrete stronger, and B, it makes it less susceptible to acid attack or alkali silica reaction damage. And number 4, air voids in concrete, again, improve cohesion and overall reduces bleeding in the fresh concrete. So those are the good aspects of air voids in the concrete. Here's the bad. Number 1, the more air voids you have in the concrete, you're increasing the porosity and permeability of the concrete. That's good up to a point. The porosity is good up to a point. Permeability is basically not so good, because the more permeable your concrete is, the more susceptible it is for aqueous solutions, watery fluids with maybe some nasty chemicals in it that might harm your concrete. Number 2, exactly what I said. and number 3, as I mentioned before, if you have too much air in your concrete and you're reducing its weight too much, you're reducing its overall you reduce overall strength by too much air in the concrete. To drive that point home, let's take a look at this. Let's quickly take a look at this graph. On the y-axis, we have PSI, strength, from 1,000 to 7,000 PSI, and on the x-axis, we have the water to cement ratio from a 0.4 to a 0.8. And the 5 different curves are representing the strength of the concrete per water cement ratio and by air content. So just to keep it easy, let's take a look at a cement that has, let's take a look at a concrete with a water cement ratio of 0.5. With 0 entrained air, 0% entrained air, we have a strength of about 4,500 psi. When you entrain it with 8% air, the strength is decreased to about 2,700 psi. So the relationship is clear. When we talk about the total percent air in concrete, we have to add up both of the major players. So the total percent air is the amount of entrapped air plus the amount of entrained air. The amount of entrained air is a variable that we can control by adding a certain amount of admixture or surfactant to it to produce the entrained air. The entrapped air is something we may not have a whole lot of control over. I mean, when concrete is fresh and when it's first placed, it will typically have anywhere from 0.5% to about 3% air just as entrapped air. Theoretically, it's possible to have concrete with 0% air. There's a special name for that. I can't think of it right now, but it's theoretically possible. Typically, it's between 0.5 and 3% air. And then if you entrain your concrete, it'll raise that total percentage up. So the total percent of air is dictated by three basic factors. First of all, the method of placement. Whether it's poured out of a truck, whether you're shoveling it out of a wheelbarrow, whether it's trammed into place, each one of those procedures will help dictate how much air is trapped in the concrete when it's flopped onto the ground or in the formwork. The degree that the fresh concrete is compacted or vibrated, right? The more you compact it, the more you vibrate it, the more you're driving the entrapped air out. And also how much air entrainment mixture you're adding, much water you're adding, those will all increase the amount of entrained air. So those three factors are definitely in play. There's always a discussion about this, and it comes up once in a while about there's a slight disparity between the total percent air measured in fresh concrete versus the total percent air measured in the hardened equivalent of that same concrete. In a perfect world, the amount of air in the fresh versus hardened version of the same concrete would be a 1-to-1 ratio, and the data would plot along that 1-to-1 line. But that's not how it is in the real world. Typically, we see a difference, maybe up to about 2% of air between what's measured in the fresh concrete versus what's measured after it's hardened. And there's a lot of debate as to why that is. I'll just throw a couple ideas out, and y'all can think about it a little bit more. But it's important to understand that first of all, the method of measuring air in fresh concrete is different than how you measure air in hardened concrete. The methods are different, the instruments are different. So right off the bat, you're working with a bit of difference just in how you're doing it, and that's probably accounting for most, if not all, of the variation. So there can be some other factors as well, but and we'll talk a little bit how hardened air can air content be different from fresh concrete a little bit later on. But basically, it's probably more of a methods and instrument issue than anything else. Big question is, how much air does concrete need, and do you need air in your concrete? Well, again, it depends on what you're using it for and where it's going. So how much air does your concrete need depends on, first of all, the climate in which you're placing your concrete. Especially ask yourself the question, is your concrete going to be exposed to freeze-thaw cycles? That's the big one. I'd submit that if you're placing concrete in Arizona, that same concrete wouldn't last very long if you placed it outside of on a sidewalk in New York City, just because of the temperature differences, the climate differences. Also, the nominal maximum aggregate size in your concrete dictates how much air you need, and as well as what you're going to be using it for. So if you're interior versus exterior concrete, there's a big difference there. Interior concrete isn't exposed to climates and might have a different overall use to it. But with respect to aggregate sizes, this is out of ACI, and I'm not going to go through the whole thing. I just want to point out the fact to you that the larger, so the left-hand column shows nominal maximum aggregate sizes from less than 3/8 all the way up to 3 inches. The other columns represent how much air you need, the percent air content, total air, for severe exposure, really heavy-duty freeze-thaw cycles versus mild exposure, not so much of a climatic variation. So, for example, if you have nominal aggregate size that is less than 3/8 inch, the concrete, they're recommending concrete have maybe up to 9% air in it, whether in severe exposure conditions versus mild exposure conditions, maybe 5% air for the same concrete. So again, it depends on the climate. That's huge. Okay, question number 2.
All set, Chris.
Thank you. Okay, so what 2 factors dictate the recommended total percent air for concrete placed outside, exterior placed concrete? D, the nominal maximum aggregate size and the exposure conditions, as we just discussed. Let's focus a little bit on freeze thaw damage of concrete. Again, the air void system in concrete is meant to combat this largely, so this is important. It's also important to understand that the ability of concrete to mitigate freeze thaw damage due to the air content was an accident. It was an accidental discovery that took place back in the 1930s. Animal fat was used as a grinding agent during some cement production, and it was realized that the use of that animal fat produced air bubbles in the paste, and exterior concrete made from this air-rich concrete resisted freeze-thaw cycles better than concrete that didn't have it in it. So it was an accidental discovery, but it was key to the whole thing. We all know, for example, that when water expands, so water gets into concrete, rain, melting snow, groundwater, whatever, right, can get into the concrete, so it has water in it just naturally. And when that water freezes, it expands about 9% in volume. We know this already if anybody's accidentally put a beverage in the freezer and forgot about it. The beverage freezes, expands 9% and blows up in the freezer. So we've probably experienced that before firsthand. What happens here is when the water expands in volume, when it freezes, it basically exerts such a strong internal pressure inside the concrete that the tensile strength of the concrete is compromised and it'll crack and eventually fail. It's basically, in geology world, it's called mechanical weathering. And again, everybody's familiar with mechanical weathering and the damage of freeze thaw. If you've ever seen how streets, how streets look with all the potholes in them after, after a winter, the freeze thaw action of the water expanding and contracting inside the road makes the potholes. It can happen with architecture as well. There's a pretty famous example of some concrete work that is deteriorating because of freeze thaw damage. Your sidewalk, driveway might be showing the same problem. So the beauty of having air voids in your concrete is that they basically act as a little pressure relief valve for when the water inside the concrete freezes and expands. The open air or the open space in those air voids act as they accommodate the pressure expansion created by the ice formation, and therefore stop the concrete itself from cracking apart. The air voids absorb the pressure. So when we're when we're evaluating the air void system in concrete, let me just take a step back and say that sample preparation is absolutely crucial, absolutely critical. And ASTM has very strict guidelines on how the sample should be prepared and how it should be at the time of analysis. So it's a big deal. To give you an example of this, I'm showing you two pictures right now, two images of the same piece of core. On the left is a concrete core that's just been cut in half lengthwise. You can ignore the magic marker drawing on there, but the core is cut in half lengthwise, and you can see some rebar inside the concrete. So that's just straight out cut concrete with a slab saw, not a chop saw. That's with the slab saw. So you can still see some saw marks. Surface is not great, but you can make out aggregates and paste in the rebar. ASTM requires that the sample be highly polished, almost to a mirror-like finish, and so that requires a lot of time and effort, and especially if there is an attention to detail, and if there are things like embedded rebar, steel embedded in your concrete, that makes things generally tougher because the hardness of the steel is different than the rest of the material in the concrete. Anyway, after the sample is polished, this is what you would see on the right hand side. So just a before and after picture of polishing. Clearly the polish is bringing out more and more details. And when you take a close-up look of that polished concrete, again, you can easily make out the coarse aggregates, the fine aggregates, the paste. If you look closely, you can notice variations in paste color around certain aggregates in certain places. So details that you wouldn't see just by cutting it open and looking at it on a fresh surface. Now you're seeing details even like that. If you squint hard enough, your eyeball might be able to pick out some of the bigger air voids. And this is just looking at it under 4 or 5 power magnification. This is just the actual sample itself. And zooming in even more closely onto that polished surface, again, we can see the paste. We can see an aggregate. The paste aggregate boundary is clearly defined. There's another aggregate down here, more aggregates here. We can start to see differences in aggregates. Here is a little aggregate particle, really fine particle with a metallic luster to it. Same here. This aggregate's different than this one, right? You can start identifying actual aggregate types if you had to, and then of course you can start seeing the air voids. Here's a big one. Here's a smaller one. Here's a one in the middle, and so on and so forth. It's also crucial to work with the lighting on these samples. A light shining straight down onto the sample surface may not show all of the details. Inclining your light source to so you have a smaller angle of incidence with your sample surface will bring out more detail, and all of the individual air voids start to look like craters, and you can actually see shading inside the void itself, which tells you it's a divot. Understand too that when your sample of concrete is cut, right, it's just it's a cut just randomly going through air voids. Some air voids will be cut directly in half. Some will just be barely missed. Some will just have the end sliced off, right? So it's also important for your eyeball to note, yeah, that's a big air void, and that's an air void, but is that an air void or the end of one, or what is that? Oftentimes you have aggregate particles that are plucked out during the polishing process, and they'll leave a hole behind, and so you need to be able to differentiate that as not an air void, but what used to be an aggregate particle. Here's a perfect example of that. Here's a large void, right? I mean, it's a void now, and there's something in it. The question I'm asking myself as I'm analyzing the sample is, well, is that the remnant of an aggregate particle that got plucked out, or is that really an air void with something stuck in it? I mean, I have to identify what that is. Turns out that this thing is an actual air void. it's full of some polishing compound that didn't get completely rinsed off the sample when I was done preparing it. So that's what that is. But that's an air void that I would include in the analysis. So again, attention to detail is critical, and understanding what you're looking at is absolutely critical. And a void left by an aggregate pop out is not something that we should consider. All right, time for question 3.
All set, Chris.
Thank you. When was concrete's resistance to freeze-thaw conditions accidentally discovered? Again, back in the 1930s. When we're evaluating the air void system in hardened concrete, this is the method is outlined in the ASTM. It's got its own number, right? ASTM C457, officially titled the Standard Test Method for Microscopical Determination of Parameters of the Air Void System in Hardened Concrete. The STM outlines, among other things, polishing, sample prep procedures, polishing procedures, what to look for, how to do it, so on and so forth. The end result of the test method is that we learn several important factors about the concrete. In other words, this test method essentially mathematically describes the air void system within the concrete, mathematically describes it. And there are 6 variables in particular that are that we'll discuss here that come up as part of the data processing game. The air content, right? The total air content of the concrete, the paste content, the paste to air ratio, something we call the void frequency, something called the specific surface, and something called the spacing factor. There are other variables. These 6 in particular we'll talk about, and ASTM has assigned some shorthand notation or abbreviation for each of these things. In order to understand what the numbers mean, I'm going to briefly walk through the 2 methods that are used to gather the data to then determine those 6 factors and the air void system in particular. The first method, again, I'm generalizing this, but we'll get the idea. The first test method is something called the linear traverse method. So in order to explain this fully, I need you to pretend that we're looking at a piece of concrete here, and the blue circles or spheres are represent air voids in the concrete. So the linear traverse method consists of a series of lines, which we call traverses, or segments of a traverse, that are equally spaced and that go across the surface that are parallel and equally spaced, that go across the surface of the cut and polished concrete. And so imagine starting here on your sample and imagining this is the line that you follow. As you're following across this line, you're noting how much of that line is essentially intersecting paste, how much is intersecting aggregate, and how much is intersecting an air void, whether it's through the middle or just barely or whatever. And you're also noting, how many voids you run across during that traverse segment. So at the end of the day, you have a series of these parallel traverses that go across the sample surface, and you add up all the data and get your answers. So the cumulative length of all these individual paths is what's called the total traverse length. And how long that total traverse length needs to be is dictated by the nominal maximum aggregate size in your concrete. Generally speaking, the bigger the aggregates you have in your concrete, the longer of a total traverse you need. So the more surface you're going to have to analyze. So for example, if your nominal maximum aggregate size is a ½ inch, ASTM requires 10 square inches of surface area to be analyzed. So imagine, 5 inches long by 2 inches wide. That's your 10 square inches, but you need to have 80 inches of total traverse length in that 10 square inch area. So it gives you an idea of how many individual traverse lines you need and the spacing between them. The second way of doing this is something called the modified point count method. And first, let me say that the linear traverse method and the modified point count method give you the same answers, right? It's just two different ways of doing it. So in the modified point count method, we're still going to pretend that we have a sample of concrete and the blue spheres represent air voids. We're still going to envision parallel paths of traverse segments equally spaced across our surface, but instead of just one continual line, each line is made up of a number of points. And basically, the same system applies here. The bigger the nominal maximum aggregate size, the longer total traverse length we have. So the bigger the aggregates, the more surface area we basically have to analyze. That also means that with this method, the aggregate size, the nominal maximum aggregate size dictates how many points need to totally analyze. So the number of points over how long of a traverse length tells you how many individual points in each of those segments. So it's just a data entering exercise at this point. So imagine looking down the microscope at each point, and for every point, equally spaced points on equally spaced parallel lines. For each point that your crosshairs stop on, you have to basically manually enter. Are the crosshairs stopped on paste? Are we stopped on an aggregate particle, or did we stop on an air void? In addition, as we're traversing from one point to another, if we transect a void, we need to record that as well. If we go across a void, we count that as well. So down at the bottom, again, a ½ inch nominal maximum aggregate size means that we still need 10 square inches of surface area to be analyzed. That means 80 square inches total traverse length. That equates out to 1,200 individual points. So again, imagine 5 inches long by 2 inches wide, 1,200 individual points equally spaced on equal spaced lines over that area. That's what you need for the modified point count method. The ASTM provides all the fancy mathematical formulas that you can then enter your raw data in to come up with the answer. You can also do it with a spreadsheet or certain computer programs. I won't go through the formulas, but once you enter the data, the raw data, here are the 6 major variables that get spit out at the end. So first of all, the air content is given, the percent air in the sample. So it's the total percent air that you can give, right? Because you're noticing the not only entrapped air, but also entrained air. Or you can just focus on the entrained air, or just focus on the entrapped air, but you basically have to run two different tests on the same points, right? To get those data separated out. That'd be one way of doing it. Anyway, the total air content of the sample is produced in the end. The percent of paste is also given. There's also a paste to aggregate ratio and so on and so forth. There's a paste to air ratio. Again, these are computed just by the raw data that you entered, or that you measured and entered from your your analysis. The fourth variable is something called void frequency, and essentially all we're doing there is determining how many air voids we cross through on any particular length of traverse. So in the example that I'm showing you above, our traverse line shown by the little red dots go through 1, 2, 3 air voids. So the void frequency for that particular length of traverse is 3. How many voids per length, voids per inch or voids per millimeter? The reports are given both in metric and English units, or English units, right? You can toggle between the two depending on what the client prefers. A fifth variable that's described is something called the specific surface, and is denoted by the Greek letter alpha. So specific surface, it's a ratio basically between between area over volume, basically square inches over cubic inches, for example. And it's essentially describing the fineness of the air void system, basically describing how small the voids basically are on average, right? So if you look at the graphic at the top of this screen, this shows us that the specific surface of a small void is greater than the specific surface of a larger one. So again, this is describing the fineness of the void system, just the overall size of the voids, which again is a function of how many of your air voids are entrained versus entrapped, right? Entrapped air will give you larger physical voids, and so you'd have a smaller resulting number. So again, average surface area of the voids in hardened concrete per unit volume of air. Think of it that way. And then the sixth variable we'll talk about, or that's computed through the air void test, something called the spacing factor, and is denoted by an uppercase L, like an italicized uppercase L. And the spacing factor, again, is probably the most important of the bunch, and it requires other data to actually compute this. Requires some of those other parameters to produce a spacing factor, but defined, it's the theoretical maximum distance from any point in the paste to the nearest air void. The maximum distance from any point in the paste to the nearest air void. Basically, how far, what's the maximum theoretical distance that that you have to travel from any point to get to another air void. So to visualize this, I've given a very simplistic example here which is basically a cubic lattice work of voids. So imagine the blue circles, or sorry, the blue spheres are air voids, and they're arranged in kind of this cubic pattern. If you imagine the distance between the maximum distance between any two voids in this array, it would be this one in the back rear top corner of this particular cube versus the one in the bottom right front corner of that same cube. That distance from there to there is the theoretical maximum distance between those two air voids. And you can't go anywhere else in this example and find a distance bigger than those two opposite corners, right? So that would be that number, either in inches or millimeters, would be the spacing factor. The idea behind this being important is that the spacing factor is essentially telling you how far water would have to travel to find a pressure release point if it started to freeze, right? So having air voids that are spaced farther apart will be less likely to help mitigate freeze-thaw damage than if they were closer together, right? There's a happy range in there between those two extremes. At the end of the day, ASTM C457 gives recommended values for these individual parameters. So again, depending on the exposure, Arizona versus New York City, exposure. Depends on the air content, anywhere from 4.5 maybe 9% based on the exposure. The paste content, it is what it is. Paste to air ratio, they recommend between 4 and 10. Void frequency, again, I'm just looking at imperial or English units. They recommend greater than 8 voids per inch. Specific surface, anywhere between 600 to 1100 square, right, area over volume, square inches over cubic inches, and the spacing factor. This is what they recommend. So in other words, these are the values that ASTM recommends for the concrete to best combat freeze thaw damage, best resist it. And of the bunch, spacing factor is probably the most important variable to pay attention to. Okay, question number 4.
All set, Chris.
Thank you. Okay, so which air void system parameter best describes the air void system in hardened concrete? Again, the spacing factor. I mean, they're all important, but the spacing factor is probably the most important of the bunch. So what factors influence the total percent air of the concrete? This I'm not going to walk through all of, there are three or four slides here, and the list isn't complete. There are a lot of different factors that are involved here, but just to give you an idea that this isn't as simple as you'd think. Alkali content of the cement, cement fineness.
Hold on one moment, Chris.
Yeah.
For some reason, it's still showing the poll.
Okay, I'll wait.
I'm not certain why it's doing this.
If it's a fatal error, Lindsay, let me know, and I can just walk through. I can just talk through the rest of these slides. If not, I can wait.
Try unclicking share screen and reshare your screen.
Okay. Show screen. About now?
I am still seeing the poll. Steve, are you also seeing the poll?
I still see the poll screen, yes.
All right.
According to my control panel, Lindsay, I'm on show screen as well as show video or camera.
I still see your video.
Are the participants noting that they can't see anything either other than the poll question?
If anyone is able to see something other than the poll, or if you're just seeing the poll. Okay, it looks like the other participants are saying they can only see the poll.
Okay, yeah, it's nothing I pushed on my end.
All right. And on my end, it's showing that it's closed. I'm trying to hide it, and that's not helping.
I would say keep going, Chris.
Yeah, I'm going to keep on going. I'll keep my slides progressing like normal, and I'll just narrate. So worst case scenario is people just hear me talking for the last couple slides. Best case scenario is you can start seeing my slides. Sound good?
Sounds good.
Okay, so basically, I was just showing some images that there are a lot of factors that dictate the amount of air that occurs in concrete, not just the addition of admixtures or surfactants or how it's placed. There are other things, other factors as well, including the alkali content of the cement, the use of water reducers, the aggregate particles we talked about already. The bigger the aggregates tend to decrease the amount of air in the mix. Total sand to total aggregate ratio, water cement ratio. I'll just list a few more. There are more. Pigments, specifically dark colored or black colored pigments, the use of those in fresh concrete will make more air. Mixing time, speed, or capacity of the mixer, agitation, vibration, temperature. If the aggregate particles have dust on them before they go into the mix. If you're using mixing water that's hard water, that has a factor. So the list is about 300 things long. There's a list of about 300 things that affect that can affect or potentially affect the air in the concrete. So I'm just letting you know it's not always an open and shut determination. One other thing I'd like to mention. People ask me quite frequently, you know, can the total percent air of hardened concrete change over time? And I'll say that hardened concrete obviously doesn't magically produce entrained or entrapped air voids once it's hardened, right? So it never increases. The air of hardened concrete never increases over time. The air voids don't magically start appearing in hardened concrete. However, air voids in concrete can over time be filled in with secondary products such as gel from alkali silica reaction, ASR gel. Water migrating through the concrete might leach out soluble components like calcium hydroxide or calcium sulfate with water and reprecipitate those soluble elements inside the air voids. So once the air voids are filled with these secondary minerals and materials, they cease being air voids, right? They're just a full solid thing at that point. So their ability to help resist freeze thaw, for example, would be nullified. And it's easy to see this even in hand sample. You may have seen a core of concrete where some of the voids are, what used to be voids, are clearly full or partially full of some other material. You might be able to dig it out with your fingernail, or it might be kind of soft, gooey, you know, white colored stuff like a hard water deposit filled in there. I mean, you can see this with your eyeball, and that has an effect obviously on the microscopic level as well, and will affect the freeze thaw durability of the concrete. So there was a fifth question that you would find, but since we can't do the polling questions anymore, we'll just skip that. But anyway, there was a fifth question which rounded out the webinar. So two things. First of all, I want to invite everybody to the next webinar that ATL is giving. It's going to be on concrete non-destructive test methods, or NDT methods, concrete NDT methods. It'll be given by Mr. Steve Moore, right? PE, senior engineer here at ATL. He's on the line with us right now. And this webinar will be given on Thursday, August the 27th from 2 to 3 p.m. Again, this webinar is Concrete NDT Methods, Thursday, August 27th from 2 to 3 p.m. So please register for that if you haven't done so already. With that being said, I'll conclude this webinar, my presentation of this webinar, but if anybody had submitted questions, Lindsay, will you let Steve and I know and we can do our best to answer them?
All right, anyone at this point, if you have any questions, please go to the questions section and submit them for us.
We'll leave this open for a couple minutes, and while you may be thinking of a question or typing one in, just let me reiterate that if anybody wants to speak with me about this topic, samples or analysis or anything, you see my email listed on the webinar, and of course from the Atlantic Testing Laboratories website. Please contact me. I'll be happy to speak with you.
All right, Chris, we do have a question. This is from Justin Raw. He says, "Thank you, Dr. Kelson, for all air void analysis. How do you ensure your selected area for analysis is representative of the whole?"
Oh yeah, that's a great question. That's a great question. So the answer is that there has to be a basic assumption in that the sample of concrete given by the client, right, for analysis, you have to assume that that's a representative sample of the greater placement, right? Obviously, in a perfect world, you'd like to have a sample of the concrete from within the center portion of the placement, away from edges, away from boundaries, right, as best you can. And once I get it in my hands, I cut it in half and try to analyze the most central portion of that sample. And again, we're going with that as being the representative example of the whole thing. That being said, if you were to submit 10 different cores for air void analysis from the same length of 100-foot sidewalk, you're going to probably see some variability in air in each of those 10 cores. It's not going to vary probably a whole lot, right, from core to core. I mean, maybe the distribution of air void theoretically is homogeneous, theoretically is homogeneous through the sample, but you don't know how it was placed. You don't know if it's the case or not. And so the more data points you have from the same placement, the more accurate your answer will be. But again, if you just have one sample to work with, you do your best to, again, collect one from the center of the placement and analyze the center portion of that. Steve, is there anything you want to add in on that question?
There are some ASTM and ACI guidelines on choosing locations, and to a certain extent, it depends on what the purpose is. Maybe you want to choose. Maybe you're seeing some failure in one location and not in another, and you want to take two different samples, one in a good area, one in a bad area, to kind of compare the two and see if low air might be the issue. Generally speaking, it depends on the purpose of the investigation.
Yeah, that's a great addition, Steve. And I'll say the same thing for any concrete that's submitted for petrographic analysis as well. Again, in a perfect world, you'd like to have a sample of the concrete that's failing, so you can directly see why it's failing, and also a sample of concrete that's not, to compare the two. So yeah, same general idea there. Yep, good, Steve. Thank you for that contribution. Anything else, Lindsay?
We do have a few more. Kim Chung would like to know what the answer for that last quick poll was, the one we got stuck on.
That was question 4.
Yes, the overall air void.
Yeah, it was spacing factor. That was of all the variables, and they're all important. Spacing factor is probably the one that we look at the most closely. Yeah, thanks.
All right, we do have a few others. Paul Griggs asked, how can you distinguish between voids from plucked aggregate particles or an air void?
Yeah, great question there. So aggregate particles are typically more angular than they are spherical. So seeing a void that has definite sharp angular edges to it is a red flag for me that that's not formed from air or water. It was probably formed from a sharp piece of rock that plucked out. Also, oftentimes when an aggregate particle plucks out of the cement, a little bit of the aggregate particle might still be stuck inside the void, and if that's the case, that's a slam dunk telling you that that's not an air void, but an aggregate piece that had been plucked out. So for those voids, closer scrutiny is definitely needed, but it's possible to do. Yeah, great question.
Next question came from Stephen Metzer. He said, nice presentation despite the tech glitch. How do we receive attendance verification for our records? And the answer to that is it will be emailed out in the next couple of days. And we have, oh, sorry.
No, we're good. I was just saying thanks for the kind words. Thank you.
Yes, thank you. And we have one more question here from Justin Roth. For the modified point count method, how would you treat a large entrapped air void that encompasses more than one of the lines of traverse, in particular when tallying the number of voids intersected?
Yeah, that's a great point too. So there is a for every data point that falls within an actual void, you record that separately from a void that's just crossed between 2 points. Yeah, and I'm not sure I fully elucidated that, but you definitely treat points that fall in voids differently than just points that cross voids. And sometimes voids are big enough that you get multiple points falling into the same void, and if that case, you just tally that again and again and again as an intersection of a void versus an interception. Yeah, that's a great question. Anything else, Lindsay?
Justin says thanks.
Thank you, and thank you all for participating. Again, feel free to reach out to me if I can help answer questions or be of service. Thank you very much. Thanks, Steve. Thanks, Lindsay.